Okay, so we're doing 1-point iteration methods, otherwise known as, for us, are going to be fixed point methods. So what we were talking about is we need a method that we can write it as x is equal to g of x, and then it becomes a fixed point. And so for a fixed point, I gave 3 examples of different ways, actually 2 examples of different ways to solve this problem. Okay, so there are other methods that we could have used as well. Actually, yes. So we did Newton's method, which was the first way. Then the second way was we just solved for one of the x's. And then the third way, we just added an x to both sides. Okay, so I was just getting ready to do a lemma. Okay, so we want to let g of x be continuous on the closed interval AB, and assume that A is less than g of x is less than B. Okay, for all x inside AB. So whatever g is, so if g is defined on the interval 0, 1, that anytime you take g of the value inside the interval 0, 1, you go back into the interval 0, 1. Okay, so what that means is g of the interval AB literally goes back into, or this whole set goes back into the interval AB. Then x equals g of x has at least one solution in the interval AB. So what does that look like? Very simple. This is the interval AB. And when I take g of any x inside of there, it goes back into the interval AB. So g of that x is somewhere inside of AB. Okay, don't know where it is, but I know it's back inside. Okay, so I'm going to prove this. All right, so let's consider a continuous function, or the continuous function. I'm going to call it f of x, and it's equal to g of x minus x. Okay, at x equals a, f of x, well, f of a is equal to g of a minus a, and I know that's greater than 0 because g of a is bigger than a. And at x equals b, f of b is equal to g of b minus b. and I know that's less than 0. So by the intermediate value theorem, there exists a C inside the interval AB such that f of C is equal to 0. So if f of C is equal to 0, that implies that G of C minus C is equal to 0, and that is the root. So C is the place such that G of C is equal to C. So it's at least 1, okay? All right, so here's a lemma. I really like this section. This is a great section. So the lemma says, let G of X be a continuous function on the closed interval AB, and assume that G takes AB, G of AB is contained in AB. Okay. Also assume there exists a constant lambda that's in the interval 0, 1, such that the absolute value of G of X minus G of Y, the whole absolute value, is less than or equal to lambda times X minus Y. So this is called a contraction function for all X and Y in the interval AB. So that means I can look at the distance between X and Y, but when I take G of X times minus G of Y, that distance is even closer because lambda is a fraction. Then X equal to G of X has a unique solution alpha in the interval AB. All right. So again, that means alpha is equal to G of alpha, and alpha is unique. Also, the iterates xn plus 1 equal to G of xn for n greater than 0, n greater than equal to 0, will converge to alpha for all x naught in AB. So it doesn't matter where you start. Once you start doing xn plus 1 equal to G of xn, you are going to go to alpha. Okay, so that's true. And we also get the absolute value of alpha minus xn is less than or equal to lambda to the n divided by 1 minus lambda times the absolute value of x1 minus x naught. And the absolute value of alpha minus xn is less than or equal to lambda to the first power over 1 minus lambda times the absolute value of xn plus 1 minus xn. Now, this is a hefty proof, takes a while to prove, so I'm just going to let you know that the proof is in the book. Should be. I think it is. Okay. So we get another theorem. So that says that, so the key thing about this first one is that if you take G of anything in the interval AB, you're going to get something back in the interval AB. So it's going to completely go around itself. That's first. G of X, because if it's a continuous function, all right, and there is if you have this lambda between 0 and 1 such that G satisfies that equation. So if G satisfies this equation, so G is continuous on the closed interval AB. Okay, G is completely inside. It maps the interval back to itself. Okay, if there exists a constant such that that happens, then we know that X equals G of X has a unique solution. Okay, and wherever you start, whatever X naught you start with is going to converge to your alpha or your root. Okay, theorem. So assume G of X is continuously differentiable on the interval AB. And that G of the interval AB goes back into the interval AB. And so we got three things here. So one, G is continuously differentiable. G takes an interval back into itself, and that lambda is equal to the max of all the x's less than or equal to b of the interval of the derivative. So we're going to define that to be lambda. So that's a triple equals. So that's how we're going to define lambda. So if the derivative, the maximum value of the derivative on the interval is less than 1, because remember, lambda is between 0 and 1. So now we're going to define what this lambda is. Then three things happen. Okay, so the first thing is that X equals G of X has a unique solution we called it alpha inside the interval AB. Now that just comes from the previous theorem because my lambda is less than 1. For all X naught in AB, with the sequence of iterates xn equaling g of xn, where n is greater than or equal to 0, we know this, that the limit, we already said it, but I'm writing it out. The limit as n goes to infinity of those iterates is equal to alpha, and 3, the other results, the absolute value of x alpha minus xn is less than or equal to lambda to the n times the absolute value of alpha minus x naught, and that is less than or equal to lambda to the n over 1 minus lambda times the absolute value of x1 minus x naught. Okay. And the limit as n goes to infinity, this is a really nice one, of alpha minus xn plus 1 divided by alpha minus xn. This limit is just the derivative of g at alpha. And so you can just put the two preceding things. So the proof of 1 and 2 are just the preceding lemmas. So the proof of 1 and 2 are the preceding lemmas. So let's prove 3. So the proof of 3 is alpha minus xn plus 1. Remember, alpha is g of alpha minus, and xn plus 1 is g of xn. But this is equal to g prime at c times alpha minus xn by the mean value theorem. Okay. So now alpha xn is going to alpha, and cn is also going to alpha. So you get the limit as n approaches infinity of alpha minus xn plus 1 divided by alpha minus xn. Well, that's just the limit as n approaches infinity of g prime at c. But c is going to alpha, so this just gives me g prime at alpha. Okay, so let's look at this as problem. So here's a nice example. We want to solve. Oh, actually, I'm not even going to go through solving. I'm just going to say x cubed plus 4x squared minus 10 equals 0 has a unique root in the interval 1.5, 1, 2. So let's let x naught be 1.5. Remember, x naught can be anything we want. All right, so number 1, let's let x equal g1 of x. So this is going to be our original. So therefore, if I'm adding x to both sides, I'm going to get x minus x cubed minus 4x squared plus 10. Okay, so actually I just took and subtracted that from x on both sides. All right. So for this problem, there does not exist an interval AB such that G prime, G1 prime of X is less than 1. So for this one, we have no reason to expect convergence. It doesn't satisfy the conditions of our lemma. So we can't say because such and such happens, this should happen. I don't have that authority. So the second one is going to be G2 of X. And this is the one where I actually solve for X squared. Okay. So when I solve for X squared, I got the square root of 10 over X minus 4X. What did I do with this one? Oh, I put 4x squared plus 10 on one side, and then I divided by x squared x and took the square root. Yeah. So this one I had x cubed, whoa. So I said x cubed is 10 minus 4x squared. And then I divide it by x squared. Something's wrong here. Oh, I divide it by x. And then I took the square root. Okay, so G2 of that. So now here's the problem with this one. So the problem with this is twofold. One, the first problem is G does not take, this G that I have does not take the interval 1, 2 back into the interval 1, 2. So that's the first problem. Then the second problem is X naught, well, Xn, this secret series sequence, n equals 0 to infinity, is not defined for X naught equal to 1.5. All right, and the absolute value of G2 prime of X is not less than 1. So that, even though I could derive that way of solving the problem, it just doesn't work for me. All right, so let's try a third way. So the third way is to take X is equal to G3. So this is the third attempt. And this is 1/2 times 10 minus x cubed to the 1/2 power. Okay. So for this one, G prime of 2 is equal to G prime of 2. Oh, okay, so that's a problem. So for this one, this fails. On the interval 1, 2, because G prime at 2 is equal to 2.12. So what we can do is we can use a smaller interval. So use this interval 1.15 instead. So just use a smaller interval. And when we do that, the hypotheses are satisfied. And in general, this will converge in approximately 30 iterations. Okay. Let's look at G4. This one is 10 over 4 plus x to the 1/2 power. And so for this one, the maximum value of G prime of any x is less than 0.15. So it's got a really small derivative. Really small derivative. So with that really small derivative, we get rapid convergence. In approximately 15 iterations. Okay. And then in number 5, Gx is equal to G5 of x. And this one is x minus x3 plus 4x squared minus 10 divided by the derivative of that, which is 3x squared plus 8x. And you should recognize this one as Newton's method. This has the fastest convergence. Approximately 4 iterations. So if you did your codes, which shouldn't have taken you too long to write, but if you did your codes, you should see how fast Newton's method and secant method is compared to the bisection method, which is very, very slow. Okay. Oops, I want you there. So we want to look at numerical evaluation of multiple roots. What do you do when you have something that has more than one root? Okay, so definition. Well, I don't want green, I want black. Okay, so f of x has a root of multiplicity p greater than 1 if you can write f of x is equal to x minus alpha to the p times some residual function h of x. All right, with h of alpha not equal to 0 and h of x continuous at x equal to alpha. So you could just factor out that part because that's how many roots it has. Okay, so if h of x is sufficiently differentiable. Okay, so what do I mean by that? Obviously, I can keep taking derivatives of f, okay, because the x minus alpha to the p is not a problem, but I need to make sure the h is. And this is sufficiently differentiable at x equal to alpha, then we're going to get that f of alpha is equal to 0. And f prime of alpha is going to equal 0. And f double prime of alpha and all the way up to the p minus first derivative of f at alpha. All of those are going to equal 0. And then, of course, the last derivative, fp at alpha, will not be 0. Okay. All right, so whenever finding a root of any function on a computer, there is always an interval of uncertainty about the root. Okay, so this difficulty or this uncertainty is worse when the root is a multiple. Okay, so we need Newton's method for multiple roots. Okay, so we already know that xn plus 1 is g of xn. That is exactly what we use. It is a fixed point method. Okay, so for Newton's method, g of xn, we already know, is xn minus f of xn divided by f prime of xn. All right, it's a fixed point. Okay, so we're going to assume that f of x is x minus alpha to the p times some h of x. And here the assumption is p is greater than 1. It can't be just, we're looking at something that has roots of multiplicity more than 1. So we can take the derivative of that. And so when we take the derivative, we get the first times the derivative of the second, whoops, plus the derivative of first times the second. Okay. So let's write that as g of x is going to be x minus, okay, in the numerator we have f, so we're going to get x minus alpha to the p times h at x. And oh, in the denominator we get all this other stuff, x minus alpha to the p times h prime at x plus p times x minus alpha to the p minus 1 times h of x. All righty. So let's factor out what we can. So now we're going to get x minus, we're factoring out x to the p minus 1. So we get x minus alpha to the p minus 1. So we get x minus alpha to the first power. And in the denominator, we're going to get x minus alpha times h prime at x plus p times h at x. Okay. So now let's look at the derivative of this function. So g prime of x, because this is what we plan to use, turns out to be the derivative of 1, which is, I'm sorry, x, which is just 1. And now I have to use a quotient rule. So that is, oh, I'm not doing a quotient rule on this thing. It'll make me crazy. I'm going to factor out the x minus alpha part. So I'm going to write this as x minus, let's factor out x minus alpha. And then we're going to multiply this by h of x over that whole denominator, which I'm going to write as p times h of x plus x minus alpha times h prime of x. Okay, so now I can use a product rule. Okay. So I get the derivative of 1 is x is 1 minus, so now I'm going to get the derivative of the first, which is 1. Oh, I have a plus there. That should be a minus. So I do the derivative of the first, which is 1 times the second. So that's going to be h of x over p times h of x plus alpha minus 1 times h prime of x. So that was the derivative of the first times the second plus, so if I just take the minus out, I'm going to do that. So I'll have plus, which distributes the minus, the first, x minus alpha, times the derivative of the second, which I am writing very nicely as the derivative of that beast, h of x, all over p times h of x plus x minus alpha times h prime of x. Okay. So now let's put in alpha. So when I substitute alpha, I get g prime at alpha is 1 minus, this in the bottom should be x minus alpha. Okay, so now I'm going to get h of alpha over p times h of alpha. And when I put in alpha, it kills the whole other thing, minus 0. So now I get g prime of alpha is 1 minus 1 over p. And remember, p was greater than 1. So therefore, this is g prime of alpha is equal to p minus 1 over p. And by golly, that is less than 1. Okay. So the convergence of this, well, let's think. Let's recall g prime. Excuse me. G prime of alpha is equal to the limit as n goes to infinity of alpha minus xn plus 1 divided by alpha minus xn. Okay. So that implies that the limit as n approaches infinity of alpha minus xn plus 1 divided by alpha minus xn is simply g prime of alpha, and g prime of alpha is p minus 1 over p. So now we get the limit as n approaches infinity. So now I'm going to take and rewrite this as alpha minus xn plus 1 is equal to p minus 1 over p times alpha minus xn. So now you should be able to recognize that this is en plus 1. This piece is en plus 1. This is p minus 1 over p. And this is en. So therefore, it's linearly convergent. And the rate of convergence is p minus 1 over p. Okay. All righty. So for this, we can improve Newton's method when p is greater than 1. Okay. So we're going to define a new g of x. And this thing is going to equal x minus p times f of x all over f prime of x. All right. And reason why we can do this is because g prime of alpha is going to equal 1 minus p times 1 over p. And then that's going to equal 0. Okay. So when you do this, you get x is equal to xn plus 1. Whoa, whoa, whoa. I don't want x, I want alpha. Is equal to g of alpha minus g of xn. Okay, remember alpha is equal to g of alpha and xn plus 1 is equal to g of xn. So this is equal to minus g prime of alpha times xn minus alpha. So I switched it for a moment. Minus 1/2 xn minus alpha squared times g double prime at some Cn. And here Cn is between Xn and alpha. So we're really using that Taylor series. That thing is good to us. So we get alpha minus Xn plus 1 is equal to -1/2 alpha minus Xn squared times G double prime of Cn. Okay, I'm a little confused here. G prime of alpha is P times P minus 1 alpha minus Xn times G prime of alpha. So that's right. I am just a little confused. Okay, I'm not sure where this came from, but I'll have to figure it out. So I got order of convergence is equal to 2. So that I know. Because this is En is equal to some C times, I'm sorry, En plus 1 En plus 1 is equal to some C times En squared. And that is why it is. Okay, okay. So I have this minus that. So when you subtract it off, it is less than that. That is why. Okay. Good. Okay. We have how many more sections in this? 2 more, because I'm not going to cover Horner's method. Oh, I do need to cover Muller's method. Okay. All right, we're getting there. We're almost through this section. Doing good. Okay. Any questions now? Because we've added another couple of techniques. Any questions on these? Okay, 10 more minutes. when we finish this, we need to have a test on the first two modules. I'm thinking sometime next week. Let's think about having a test. If not next week, the week after. Okay. All right, so let's have this polynomial P of X. And P of X is A naught plus A1X plus A2X squared all the way up to AN X to the N. And of course, we are going to assume AN cannot be 0, because if AN is 0, we're down to a polynomial of degree N minus 1. Okay, so some of the ways that we want to locate roots. So locating roots. All right, so that would take our P of X and write it as AN, and I would have X minus Z1, X minus Z2, all the way down to X minus Zn. And the Z's are our roots, and we can use the fundamental theorem of algebra. Okay, we can bound roots. And some of the rules, we can use Descartes' rule of signs. So for Descartes' rule of signs, A is abound the number of positive real roots of f of x. And honestly, guys, I don't even remember these P of X, the Descartes rule of signs. I would have to look that up again. Okay. Oh, I think I kind of got it. And then it assumes the coefficients that AI, all of the AI are real numbers. Okay. So nu is going to equal the number of sign changes of coefficients of P of X. And then kappa is going to equal the number of positive roots of P of X. And so kappa has to be less than or equal to nu. And nu minus kappa is even. So that kind of helps us figure out what we're working with. So here's an example. Suppose we have P of X is equal to x to the 5th minus 2x squared minus 3x plus 1. Okay, so the number of sign changes. All right, so let's see. We go from here, from positive to negative. So that's 1. We go negative to negative, no. And then we go negative to positive, so that's 2. So nu equals 2. Now we know kappa is less than or equal to nu. So that implies that kappa can be 0, 1, or 2. But nu minus kappa is even. So that implies that kappa is either equal to 0 or 2. Okay, so that's the number of possible positive real roots. Okay. So that just gives us a way of trying to figure this thing out. It's either 0, no real roots, or it has 2 real roots. Okay. No real roots or 2 real roots. So that means it could have all 5. So, let's think about this for a moment. 2 positive real roots. Yes. Okay. All right. And then C, we can get a bound on the negative real roots. Of P of X by bounding the number of positive real roots of a new function Q that I'm going to call P of negative X. All right, so what does Q look like? So Q says put negative X into the X to the 5th. Good. So that's going to give me negative X to the 5th. And then I'll put negative X in there, I get minus 2X squared. I put negative X in there, I get plus 3X plus 1. So that's Q. So now I have to look at the number of sign changes. There's only 1, which is right here. So therefore nu is equal to 1. So that implies K can be equal to 0 or 1. But nu minus K is even. So that implies that K is equal to 1. So therefore there's 1 negative real root. Okay. So now we have 1 negative real root and either 2 positive real roots or 4 complex roots. Okay, so that's what we know so far. I don't think I literally have 2 lines and we're out of time. Okay, so the possibilities, I'm just gonna write this down right now. I hate stopping, but we have to. So the possibilities that is one negative root. Okay, so let me write it like this. R1 is less than 0, R2 and R3 are greater than 0, and then R4 and R5 are complex conjugates. So that's one possibility. And the other possibility is that R1 is less than 0, R2 and R3 are complex conjugates, and then R4 and R5 are complex conjugates. Okay, I'm going to stop here. We have one more little thing, but I'm going to stop because we're 1 minute over.